All right, in this next section, 7.7, we're going to start talking about improper integrals, which is a pretty interesting area, and we start to take a look at some more interesting, different ways to argue, and I really think it is an interesting section overall. The content here is pretty good. So improper integrals, essentially an integral that's an improper integral is a definite integral where one of two things happens. And here we have an example of each scenario at the very top of this page here. So for these two, each one's an example of how an integral can become improper. So the first one here, this is an improper integral because our domain of integration, our bounds, if you consider that as a subset of the real number line, it is unbounded. It goes on forever. Our interval has infinite length. Okay, so that's one way an integral can be improper, that the domain of integration is unbounded. Its measure is infinite. The second way that an integral can become improper is when the actual function that we're integrating. See, our interval of integration here is 0 to 1. That's perfectly fine. That's bounded. As a subset of the real number line, that's just from here to here. That's it. So there's no issues with our domain of integration, but rather our function of the function that we're integrating can cause some issues. In this case, if we take a look at our lower bound here of 0, our function, the integrand, has a discontinuity at x equals 0. So as x goes to 0 from above, right, because if we think of this as our range of numbers 0 to 1, we are only considering in this little area, so the only way we can approach 0 is from above. So if you take the limit as x goes to 0 from above of 1 over square root of x, this goes to positive infinity. So the function becomes infinitely large. So you either have a scenario like one of these two examples. Either the domain of integration is infinitely long, infinitely large, or the function itself, its value becomes unbounded. It grows and grows and all right. So the way that we are going to handle this situation is essentially it's a little clever workaround, but we are simply, if we start with a function like this and we see that one of the bounds is infinite, so we're essentially going to just talk about this first case for now, then what we're going to do is take the infinity away and replace it with some finite yet arbitrary number, let's say r, so we essentially give it a placeholder. Then we'll calculate this quantity, so it will become a function of r, effectively. This right here will be a function of r once we plug in and substitute our bounds. Then we take the limit of that expression as r goes to infinity. All right. Let's get started with taking a look at example 1 then. So determine whether the following integrals converge, the following integral converges. So for this one, if it does converge, let's go ahead and determine its value. So for right now, we don't have any other tools to determine whether or not a integral converges other than calculating it and showing that it explicitly converges, because we calculated the antiderivative, we plugged in the bounds, creating a function of that arbitrary parameter capital R, and then we took the limit of that expression, and that limit exists. That would be the way to show that it converges. We will soon we will soon introduce another tool that will be very powerful called the Comparison Theorem, but we're not quite there yet. So to do this, we will swap out the infinity for some placeholder parameter. It doesn't matter what you call it. I'll stick with the notes and call it capital R, but it doesn't have to be R. And we have e to the negative x dx. Well, we know how to integrate this. So this is negative e to the negative x between 0 and r. Plug in our bounds. So it's become negative e to the negative r minus minus, so plus e to the 0. So we have the limit as capital R goes to infinity. And then let's simplify this. E to the 0 is 1, so we have 1 minus 1 over e to the r. Well, we know from Calc 1, then when we take the limit of 1 over something that's getting larger, right, e to the r, this is an increasing function. This is the capital R axis. There's what e to the r looks like. So 1 over e to the r, if the denominator grows and grows and grows, then 1 over that thing growing will get very small. Very small. So this goes to 0. This term goes to 0, I should say. So what we're left over with is 1 minus 0, which is 1. So the procedure in and of itself is not that difficult. We just swap out the problematic bound, whether it's infinity up here or infinity down here. We swap that out with a parameter, call it r, let's say. Doesn't matter really, but we call it r. And then we do the integral as we normally would. And there's no problem with r because r is just some arbitrary parameter. Then we take the limit of it. So replace, evaluate, and that's it. Example 2, determine whether the following integral converges. If it does, determine its value. So I'm going to go ahead and rewrite this as the limit as r goes to infinity of the integral from negative r to r, 1 over 1 plus x squared dx. Which this becomes, we know what the antiderivative of 1 over 1 plus x squared is. That's arctan. So this would be inverse tangent or arctangent of x between negative r and r. Evaluating this would be tan inverse of r minus tan inverse of negative r. Well, tangent and its inverse arctangent are odd functions. So recall for an odd function, so if a function, let's say f, is odd, then what does it mean to be odd? Well, a function is odd if and only if, let's write it this way, f is odd if and only if f of negative x equals negative f of x. So what this means is since tangent and inverse tangent are odd functions, then the inverse tangent of negative r is equal to negative the inverse tangent of positive r. So what does this mean for us? Well, this means that we have essentially this negative and this negative. This negative will come out since this is an odd function, but then we'll get a double negative, so we really just have two of them added together. So this would become 2 tan inverse of r. And we should know from pre-calculus or Calc 1 and periodically being reminded of this again and again, arctangent has two asymptotes, two horizontal asymptotes. As we go to positive infinity, the horizontal asymptote is pi over 2. So this would become 2 times what the limit of inverse tan is. Well, since limits at infinity are equivalent to checking to see if such a function has a horizontal asymptote, then we just report back the horizontal asymptote in that direction towards positive infinity. So the answer here is pi. Because we got finite numbers for this example, a finite answer for this example and for the last example, when you get a finite number, that means your integral converges. So each of these converge.